Welcome to part 2 of our screencast on chi-square and significance testing. We spent most of part 1, maybe all of part 1, talking about significance testing and some of the background information related to that is going to be relevant for us as we move forward in this part of our screencast. Now I want to talk more specifically about what a chi-square test is, specifically a chi-square test of independence, or when you're using cross-tabulations as a start. A chi-square, and it is notated as chi, that's the Greek letter chi squared, is a number that compares the actual frequencies in a bivariate table with the frequencies we would expect if there were no relationship between the two variables in the larger population. So you've got a bivariate table, and it will be split up many different ways, that is from your sample data. And then imagine that there were another bivariate table that was in the population, and there's no relationship. In other words, the null hypothesis is actually verified. So you're trying to compare what you see in your sample with what you would see in this expected no relationship population. And if we were to think about choosing the correct inferential test, remember we start with data type. We're talking about categorical or nominal data. And in our case, and I apologize, it's kind of cut off down at the bottom here, we have two variables, and we're doing what is called on here a chi-square test of independence. We're also calling it a chi-square test of statistical significance, or a chi-square test with categorical or cross-tabulation data. And there's another kind of chi-square, this goodness of fit test, that we're not covering in our explanation here, and we probably won't cover it in this class, but it is also important. For us, the chi-square test of independence is the key one, though. So what is the logic behind a chi-square test of independence? Well, if the observed frequencies in a bivariate table based on sample data are similar to the frequencies we would expect if there were no relationship between the two variables in the population, then we cannot reject the null hypothesis of no relationship. And ignore that. It's a whole other text that I don't want to talk about. So we are considering observed frequencies in a bivariate table based on sample data. And we're considering what those frequencies would look like in the population if we expected that there was no relationship between those variables in the population. So we can ask a simple question. Do observed sample frequencies look like frequencies in a bivariate table that's based on expected population data? If our observed sample frequencies look like the expected no relationship population frequencies, then we cannot reject the null hypothesis. However, if the observed sample frequencies look different than the expected no relationship population frequencies, then we can reject the null hypothesis. It is a logic problem a little bit, and I hope you're sticking with me on this. But let's look at an example and see what it looks like. So for example, here we have a 2x2 table, a bivariate table, variable 1 and variable 2. That's what bi means. There are two variables. And we have a frequency for each of the cells. There's clearly a value for variable 1 in this column and in this column, and there's a value for variable 2 in this row and this row. And let's say that's value A and value B. This is value C and value D. So for value C, a variable 2, and value A, a variable 1, we see 2. There's an observed frequency of 2. For value C and value B, observed frequency of 8. And you see how this goes, right? If there was no relationship between variable 1 and variable 2, we would expect everything to be the same, right? There's nothing going on. Everything is relatively evenly distributed. So in a bivariate table, each independent variable category would have the same proportion of cases if we expect no relationship, right? The same proportion of cases in a bivariate table if we expect no relationship. So what we can do is we can start now combining our significance testing and our chi-square logic to actually run through a chi-square example. Now, there are 7 steps for testing the null hypothesis that I'm not requiring you to go through explicitly for the calculations or the statistical computations that you'll do for this class. But I do want you to understand that they exist and that there's a logic there, and you can use them if you'd like to. So they're very straightforward. State the null hypothesis in symbols and in words. State the alternative hypothesis in symbols and in words. Choose an alpha level, which is also called a p-value. State the rejection rule. Compute the test statistic. Make a decision by applying the rejection rule, and then conclude something. Right? Write a conclusion statement in the context of the problem. So let's look at each one of these steps using an actual example. So this is an example I used at the beginning of class when we were just thinking about what statistics look like. In the United States, in the 1980s, there was a Secretary of Education named William Bennett. And former U.S. Secretary of Education William Bennett released a report contending that money was unrelated to achievement. Bennett observed that some of the states with the highest SAT, that's a college entrance examination in the U.S., with the highest SAT averages were low spenders, while some of those states that spent the most money had low SATs. For example, North Dakota, South Dakota, Iowa, Utah, and Minnesota were all low spenders on education with high SAT scores, while New Jersey spent more per child than any other state and finished only 39th among states for SAT averages. By the way, I want to point out that when we were talking about this early in the class, we found all sorts of inconsistencies and alternative explanations for why there seemed to be this relationship, this negative relationship between spending and SAT scores. So I'm not trying to validate William Bennett's conclusions. I'm trying to say that we can actually test this. So look at the actual data. First of all, let's assume that our population for this analysis is every state or nation state where people take the SAT. We have a sample of the 50 American states, but that doesn't include Canada, Mexico, or other nation states where the SAT is taken, but we can make that assumption. Right? Now, given this frequency table, how can we find the expected no relationship frequency for each cell? Remember, this is our sample. But we want to compare it with an imaginary table that would look like this, that would have the frequencies in each of the cells that would represent a no relationship between SAT average and education spending. Well, it's a pretty straightforward way to do it. If you divide each row total, here's a row total, here's a row total, by the grand total n, here's the grand total n, and you multiply that proportion, so let's say 33 divided by 50, and then we multiply that proportion by the column total, which is, in the case of this column, it's 12, that will give you our expected no relationship frequency for that cell. So for this one right here, 33 divided by 50 and then multiplied by 12 gives us the expected no relationship frequency for that cell. Okay? I guess maybe I'm going to show you how to go through this in a little bit, so don't feel that I'm leaving you high and dry. I just wanted to explain that there's a very simple calculation. We're just looking at totals of rows and columns and putting a proportion together for our row total and our grand total and multiplying it by our column total to get what we would expect to be a no relationship frequency. And then we can compare that no relationship frequency to our actual data. But let's start by walking through those 7 steps of hypothesis testing. So the first thing we want to do is state the null hypothesis in symbols and in words. So the null hypothesis is that the mean SAT scores of states that spend little on education is the same as the mean SAT scores of states that spend a lot on education. All right? State the alternative hypothesis in symbols and in words. Okay. The mean SAT scores of states that spend little on education is not the same as the mean of those states that spend a lot on education. And so we have, the big difference is this. In one case, in the null hypothesis, there's no difference. In our alternative hypothesis, there is a difference that's not equal. It's that straightforward. Then we choose an alpha level or a probability value. We're going to say that 0.05 is as high of a risk that we're going to take of committing a type 1 error. So we need a p less than 0.05 in order to say that something other than the null hypothesis is happening. Now, how do we interpret chi-square values? Well, first of all, we don't have a random sample. Since we took all of our 50 American states for our sample, let's pretend that it's random just so we can do this. Let's pretend that we have parametric data. But we don't. And we can ask, what's the probability of getting a chi-square of at least a given size, at least a certain size or strength or number, even if there is no relationship between two variables in the larger population? Okay? And that, in order to do that, we first have to establish our degrees of freedom. How many rows and columns do we have in our spending versus SAT score example? Well, we have 2 rows and 3 columns. And let me just go back to that table so you can see what I mean. Okay. 2 rows, 1, 2, and 3 columns, 1, 2, 3. Okay. So our degrees of freedom are going to be the number of rows minus 1 times the number of columns minus 1. Remember, we're not counting the total rows or columns. And we can look for the critical value of chi-square, much like we did when we were talking about t-tests. Now remember, you don't have to do this because of the magic of SPSS. Right? Our statistical software program, whether it's SPSS or Stata or SAS or you name it, does all this for us. But if you were hand calculating this, you'd look for the critical value. And remember, if you calculate a value that is larger than the critical value at a given probability level, and we said p equals 0.05, or alpha needs to be 0.05, right? We need to find a computed chi-square for the 0.05 level that is greater than 5.991 in order to say that there is a reason to reject the null hypothesis. Okay. So this table, just to go over it again, shows the minimum value of chi-square that's needed to achieve significance at the 0.05 level, the 0.02, 0.01, and 0.001 levels. Now eventually, we're going to calculate this, and we're going to find that our chi-square is 4.4075. That's our computed chi-square. That's supposed to be COMP for computed. Oh well. Our chi-square of 4.4075 is not equal to or higher than 5.991. So we're going to fail to reject the null hypothesis. But remember that there is this sort of a logic to comparing our computed value to the critical value to see if there is a statistically significant result. Okay. Now, what does it mean, by the way, when we aren't able to reject the null hypothesis? Well, for a chi-square, it means that we could have gotten the frequencies that we observed in our sample data just by chance, even if there's no relationship between the two variables in the larger population. But that's important. So let's move along. I jumped ahead just a little bit, but let's keep plodding through. Let's next state the rejection rule. We're going to reject the null hypothesis if the absolute value, that is usually symbolized like this. Right? Here's the value x, and then we put these little bars on either side, and it tells us that even if it's negative x the absolute value is positive. Ignore that for a minute. Okay. So we're going to reject the